If this is the Earth, and we have a point mass on the surface of the Earth of little m, what is the gravitational attraction between this point mass and Earth? According to what we learned, that a spherical symmetric distribution, that we can assume the total mass is concentrated at its geometric center. So we can assume that the mass of the Earth is concentrated at this point, which is one radius of the Earth away from the point mass of little m. Since we have 2 point masses now, the gravitational force between these two can be written as f of g equals to time constant, mass of the little one, mass of the Earth, production, divided by their separation squared. That is RE of square. Now, what if we have a tunnel through the Earth? That little m actually gets into this tunnel, and which is a certain distance away from the center of the Earth, but it is less than the radius of the Earth. Let's decide this one be a little r. Right now, the little r is less than the radius of the Earth. What is the gravitational attraction now between the Earth and this point mass m? Let's name it m prime. Well, this is a little bit strange situation. Let's take a look what happens. As a matter of fact, if we look at this line, all the mass above this line will attract m prime upward. So the net force is up. And all the mass underneath this line will attract this m prime downward. Well, we have more mass underneath this line, but further away. And we have less mass on the top of it, but it's closer to the m prime. As a matter of fact, we can use calculus to prove that actually the net force from the top and the bottom eventually comes down to such a situation that if we redraw this Earth, and this is the radius of the Earth. Now, if this m prime located here, we can simply use the little r to draw a core. And as a matter of fact, the net force attract m prime will come from this core. So for the little m prime, that core behave like a little Earth. So m prime is outside of this core, and the mass of the core we can still consider concentrated at the center. Now, since this is a symmetrical distribution, so we can find the mass of this core. Let's name ME of prime because this is a new one. It should be proportional volume. So if I use ME prime divided by the mass of the Earth itself, and it should proportional to the volume because density is the same. Therefore, we can have volume is 4/3 pi r cubed. So actually is this little r over RE, that ratio of cube. We can find the mass of the core, ME prime. Therefore, the force between the M prime and this core can be easily written as that FE prime equals to that capital G, this little mass M prime, MME of prime, divided by, right now this is outside of the core, and the radius of core is R, so we still treat the situation as the first one because M prime is outside this core, so the gravitational force actually has come from this core. The outer layer, the force cancels out. Okay, so if we plug in what we have for ME prime, ME primes come from here, that is little r over RE of cube times mass of the Earth and divided by r squared. And we get a very interesting situation. Let's take a look. Constant, m prime is the mass of this point, and me is total mass of the Earth, and re is the radius of the Earth. So we have little r cubed divided by r squared. So it is a group of constant that is capital G m prime of me divided by re of, that's a cube, n times r. We get a situation that gravitational force from the core to the m prime is proportional to the radius. This reminds us a simple harmonic motion situation, because right now that the gravitational force is pointing to the center of this core. So this is a kind of like restoring force, because if I draw this picture clearly again, this is the direction of the radius direction, and m prime right now is right here, and the force Fe of prime is pointing to the center. That is kind of a restoring force, and this force is proportional to the displacement, because right now m prime is little r away from that equilibrium position. So according to what we learned, F equals to ma. What we have is, this is restoring force. That's why it's negative, because it's opposite direction of the r direction. Negative g m prime me over re cubed, and r equals to ma. Right now, since the motion will be linear, that a will be dr dt of second derivative. So if we define this is a constant, and let's take a look. If we define this as constant k, and move this negative term to the left side, what we have is dr dt second derivative, and we divide by m, and both sides of the equation, we will have plus k over m of r equal to 0. This is a simple harmonic motion equation, because that we learned from the previous chapter. So it is very interesting that the particle m prime, as a matter of fact, will perform simple harmonic motion. Why is that? Because at this position, the force is pointing to the equilibrium position. So m prime will start to accelerate. So the speed will actually increase. Right at the center, since r equal to 0, when r equal to 0, force equal to 0, which means no more force. No more force only means no more acceleration. But this m prime accelerated, well, acceleration magnitude is not a constant, but acceleration is there. So the speed just gradually increase. So at this location, speed is the maximum. That's why m prime cannot stop or continue to go to the other direction. And let's take a look at it, this situation. If m prime goes to the other direction, now the speed is this way. However, now the attraction force will go up, will point to the center of the core. So that force will behave as a deceleration force. So that's why m prime will slow down, slow down, slow down until reached final speed 0. And this force is still there. Therefore, m prime will start to accelerate towards this direction. So this is just like a spring system situation, that when a mass passes the equilibrium point to the other side, spring get compressed. So spring will resist this mass, and mass will slow down. But eventually, when the mass reaches the far left end, and the spring will push it back, so it will start to oscillate back and forth. And we can find the period oscillation from the constant here, because according to what we learned from simple harmonic motion, that omega squared equals to k over m, and omega defined as 2 pi f, and 1 over f is t, that is the period. So as a matter of fact, if we know all the constant here, and as a matter of fact, we can find the omega. If we find omega, we find the frequency. That frequency is the frequency of oscillation, and we can find the period. It is roughly around 84 minutes for a round trip. Okay, let's look at another problem. This is a ring. of mass uniformly distributed. This ring has mass of, let's have capital M, radius r. Therefore, the linear density of this ring can be calculated by that mu equals to mass divided by the circumference, which is 2 pi of r. Now, there is a point mass of little m. How far away from the center of the ring? Well, first of all, x-axis is perpendicular to the plane of the ring. And so that's why this is a 90 degrees angle. And how far away is this? Well, let's assume this is a distance of a away from the center of the ring. The question is, what is the gravitational attraction between the ring and this point mass m? Now, probably you will think, well, this is a ring and this is a symmetrical object. But don't forget, this is not a symmetrical spherical object. Only the symmetrical spherical distribution that you can consider the mass concentrated at the center and then treat as a point mass to calculate gravitational attraction with as a point. And now this is a ring. It's not spherical. So what we can do is we still have to use Newton's law of universal gravitation. That is F of g equals to capital G, a point mass m1 times a point mass m2 divided by their separation square. And we have to start from there. So let's cut a piece named dm. That is a very small piece. That is a point mass. Now, this dm is point mass and this little m is also point mass. So they're going to attract each other. How? The attraction is on the line of their connection. So if we consider the attraction that dm give to m, then that force is this way. Let's name df, tiny little force. Let's name dfg, it's gravitational attraction force. Now, if we cut a piece on the top, we can always find a symmetric piece, that of dm underneath. And so therefore, you can imagine, if we connect that, there is a similar dfg that this piece of dm gives to that point mass m. Since this is a symmetric situation, then the dfg on the top, the magnitude, equals to dfg underneath. So as a matter of fact, if we look at this situation, we have a d of fg this way. This is the x-axis, and this is the angle of alpha, let's say. And then we have another dfg of same magnitude and same angle with respect to x-axis. This is the x-axis. The net force of these two will be at opposite direction of x-axis, point to the center of the ring. So actually it is the dfg of cosine alpha survives. The dfg sine alpha, this component cancels with the other dfg sine alpha. So the resultant of these two is twice of the dfg cosine. This tells us, as a matter of fact, if I cut another piece of somewhere else, let's say here, and you can find a symmetric point there, all the resulting pair will eventually point to the center of the ring, and all time at cosine alpha. So the net force between the ring and this point mass m, f of g, as a matter of fact, is the summation of the all dfg times this cosine of alpha. Now, this cosine alpha can be written as side adjacent, which is a, it's a constant, divided by the hypotenuse, which is, this is the radius of the ring. So that should be r of square plus a of square and square root. A square, r square, square root give us this. So cosine alpha is this, and it's a constant. So how do we find the total fg? Now we have to express dfg. DFG, it is a force between 2 point masses. One is the dm, the other is the m. Okay, so we have this capital G, point mass m, and dm divided by their separation square, which is r squared plus of a squared. So if we plug in this expression dfg into here, what we have is, as a matter of fact, gm, and this is all constant. So as a matter of fact, we will have this capital G, m as constant, and cosine alpha as that. So we have a, and denominator we have r squared plus a squared of 3 to the 2 and dm. So it is very interesting. The summation, which is integral, comes down to adding all the dm. You add all the dm on the ring, that's the total mass of the ring, capital M. So the result is G, little m, capital M, over, I'm going to write this, of r squared plus a squared, and a divided by r squared plus a squared square root. Why I'm doing this? Because I want you to take a look at the dimension. Here we calculate gravitational force Fg. According to Newton's law of universal gravitation, no matter what happens, the units should be capital G, kilogram square and meter square. So capital G, this kilogram square, this is a meter square. So this is the force in Newton. And here obviously is dimensionless because meter square plus meter square, that's meter square square root, that's meter, meter, meter cancels. As a matter of fact, this is a cosine alpha. That is dimensionless. So let's take a look at one more time. If we mistakenly assume the mass of the ring is concentrated here, and this is mass of the ring, if we assume, and then that little m is a meters away. If we treat this way, then the gravitational attraction between the ring and m will be, first of all, direction will still same, but the expression will be Fg equals to capital G, mass of the ring, mass of this guy, divided by a squared. That is totally different compared to what we learned, what we did integral from here. So again, I want to point out, this is wrong. You cannot assume mass of the ring concentrated here to attract the other one. Well, obviously, if you talk about center of mass, yes, center of mass, you can assume mass of the ring. Right now, we're doing gravitational attraction. Remember, only the spherical symmetric distribution. You can assume the gravitational attraction mass concentrated at a geometric center. The ring is not a spherical symmetric distribution. So you have to cut a slice of the m and to find out what is the attraction between this point mass and that point mass, and that is our df situation. Eventually we figured out we have to add all the x component of the gravitational attraction and we'll get the net force. Let's look at another problem. This is a thin disk of mass capital M, radius r. This is a disk. So it's two-dimensional. Now for a thin disk that we can assume is two-dimensional, the density of sigma equals to total mass divided by total area, which is pi r squared. Now this is a z-axis, which is perpendicular to the plane of this disk. If assume that b distance above the origin of z, we have a mass little m. The question is, what is the gravitational attraction force between the disk and that point mass m? As you know, again, this looks symmetric, but this is not a spherical object. So we cannot assume the gravitational attraction mass of the disk concentrated here. So what we need to do is we need to cut a piece from the disk, name it dm, and we're going to calculate gravitational attraction between this dm and that point mass m. Well, it's on the line of connection first. Well, if we consider the attraction that little m give to dm, then that force dfg should be that way. And where do we cut this dm? We say that is little r away from the center of the disk. The restriction for little r is more than or equal to 0, less than or equal to radius of the disk. You can cut anywhere. And angle, obviously, you can cut anywhere, so the restriction for the angle is more than or equal to 0, less or equal to 2 pi. What angle does that angle mean? For example, if this is our x-axis, if that angle is 0, and then we go counterclockwise. So if we go to the negative x direction, that is 180 degrees, that's pi radian, and when you come back, that is 2 pi radian. So you can cut anywhere around on the top of the disk. That is the angle definition. Okay, so as you can see, we can find a symmetric piece, which is also r distance away on the other side, and also dm, and on the line of connection, we will have the gravitational attraction between little m and that dm. That's called dfg. So you can tell the net force of this pair of dm, between this pair of dm and that point mass m, actually is towards the positive z direction. So how many pairs do we have? Many, many, many pairs. But we are sure the resultant force between this little m and the disk is point to the positive z direction. How do we start from here? We need to express our dfg. So we have our dfg, which is equals to capital G, that is between the point mass little m and dm, and divide by their separation square. Let's look at what's their separation. Separation is between here and here. So if we say this distance from the center of the disk to the m is b, this is little r, that's r squared plus b squared, square root is the separation. But don't forget, Newton's law of universal gravitation, we'll have to divide by separation square. So that is that. How do we express dm? This dm is a slice that we cut from the disk. So as a matter of fact, we can use a polar coordinate. That is, dm is the two-dimensional density times the area we cut. If we use polar coordinate to describe dA, that should be r dr d theta. Why is that? Okay, let's take a look. If I have a circle, and this is the r direction. Now, if I cut somewhere right here, this angle is theta. And how far away I cut? Little r away. So therefore, if the radial direction is little r, then this much will be dr, because that's the variation around the r. On the other hand, then this is around the circumference direction, that is dl. dl, the circumference dl, has something to do with how far you cut, that's r. And if this is the angle theta, then a little variation around the angle is d theta, so it's r d theta. So the circumference dl is r d theta. And then this is dr. Since this is a very small slice that we consider this is a rectangle shape, therefore the area is simply this is called length, dr, times width, dl, and we plug in dl as r d theta. So we have this, the combination will come out as r d theta. So this is quite useful equation, that the expression of area on a polar coordinate. Polar coordinate means you use the radius and angle to express, that's two variables for the two-dimensional coordinate. So we have expression of mass is two-dimensional density times dA. Okay, let's come back to this situation. Now, as a matter of fact, what we want is the z component. So if we have this the force dfg is this direction. If we want to have positive z component, we have time a cosine of this angle. Let's name this angle alpha. This angle alpha is the same as that alpha. If we want to time a cosine alpha, we have cosine alpha. Look at this right angle triangle. That equals to b, side adjacent, divided by hypotenuse, which is r squared plus b squared square root. So it comes down to that the gravitational attraction between point mass m and the disk is the summation of all the dfg times a cosine alpha. So times a cosine alpha. Now let's look at expression. If we bring dfg is right here, so that will be capital G, little m. dm is rho dA is this. So we have this sigma r d theta that give us, and then we have the r squared plus b squared. Don't forget we have a cosine alpha, and cosine alpha has this expression. So the cosine alpha bring us a constant b, well, for the numerator, so we can actually keep this b outside so we can get less confused. And then we have a square root underneath, so that will give us 3 to the 2. This is not a difficult integral. That is because constant. R dr. As a matter of fact, if we time a factor of 2 divided by factor of 2, 2r dr is dr squared. So we can rewrite this equation as, we'll bring all the constant outside. We have this capital G m sigma b, gm sigma b, and here's a 2 as, and then we have 2r dr, that is dr squared, and we have this r squared plus b squared, 3 to the 2, and we can insert a sign of integral because the theta and dr is independent, so the theta. The angle change, if you want the entire disk, we're talking about the attraction between the entire disk and point mass m, so it's 0 to 2 pi. For the variation radius, that is from 0 to r. So you can see this is not difficult at all, because we learned that because this b is a constant, so this is equivalent to, you can add a constant. You can always do that. So imagine this is du over u 3 to the 2, an integral. That's not hard at all. And this integral simply will come out as 2 pi. So eventually you will be able to find the result of the net force between a thin symmetrical disk and point mass m, which is b distance on the z-axis, which the z-axis is perpendicular to the plane of the disk. Now let me introduce a concept called escape speed. For example, if this is Earth, and obviously this is radius to the Earth, and we assume mass, gravitational attraction mass is concentrated right here. Now if there is a space vehicle or a rocket on the surface of the Earth of mass m, now we want this space probe goes to Mars. So theoretically, this space probe should escape Earth's gravitational field, which means, relatively speaking, it's not going to be trapped by the Earth's gravitational force. It's going out. So the question is, what is the VESP? What should be the escape speed? How large the force has, the speed has to be, then this rocket will be able to get out of the Earth's gravitational field. Why we need high speed? Because if we have a high speed, and then the rocket will be able to going up, but gravitational force will try to decelerate. So we'll have to let this guy keep going to very far away when the gravitational force is so weak there's no more deceleration. And that moment, if we still have a little bit speed left, then we escape. So the extreme condition is we start with a V escape and going far away from the center of the Earth with deceleration because Earth's gravitational force will decelerate. So the speed will slow down, slow down, slow down until to the edge of the Earth's gravitational field. The speed is 0, but no more gravitational attraction force from the Earth. And then we say escaped. So this is a rather difficult situation if we try to use force, because force changes magnitude all the time. So therefore, the deceleration is not a constant. But if we use energy to deal with this problem, probably that would be easier. Let's say that right here, what is the total energy of this rocket? Don't forget, if we talk about mechanical energy, we have to consider about the kinetic energy plus potential energy. In this case, potential energy is the gravitational potential energy. We learned that the gravitational potential energy between 2 point masses is that gravitational potential energy equals to negative g of first mass times second mass divided by their separation. Now, if this is a spherical symmetric object that we can view gravitational attraction masses right here, then their separation will be 1 RE. So the gravitational potential energy of the rocket has right here is negative capital G, mass of rocket, mass of the Earth, and their separation is 1 RE. And if the rocket has escape speed, so it has kinetic energy 1/2 of m VESP of squared. That's the total mechanical energy when the rocket is near the surface of the Earth. And then when the rocket is going very, very far away, very, very far away means R is almost equals to infinite with respect to the radius of the Earth. So when this R is infinite, the gravitational potential energy from the Earth will be 0. And also I explained that when you reach there, the speed is almost 0. So at that escape, the edge of the Earth's gravitational field, potential energy 0, kinetic energy 0. Why we have initial mechanical equals to final mechanical energy? That is because there's only, if we ignore the friction of the rocket has experienced with the Earth's atmosphere, which is very briefly, then there's only one force between the rocket and the Earth, that is gravitational force. Gravitational force is a conservative force, so the mechanical energy of the system is conserved. So we can easily discover that this m, you can actually, both sides of the equation divide by this little m, it's gone. And we rearrange this negative term to the other side. So we can have VESP equals to twice capital G, mass of the Earth, and divide by radius of the Earth and square root. If we plug in the proper number for capital G, 6.67 times 10 to the negative 11 of SI unit, mass of the Earth is 5.98 times 10 to the 24 kilogram, and RE is 6.4 times 10 to the 6 of meter. And we can find that escape speed, in order to escape Earth's gravitational field, it comes out as 11.2 of kilometer per second. The rocket must have enormous speed to escape the Earth's gravitational field, because every 1 second it has to be able to travel near 11 kilometers. This is a very interesting situation. If you still remember the problem that we encounter between a ring, a point mass. Okay, let's look at the situation again. This is a ring of mass capital M, radius r. This is a ring, so it's one-dimensional. Again, the linear density mu can be calculated by total mass divided by the circumference of the rings, 2 pi of r. Now the question is, if I have a point mass of little m at the center of the ring, well, if this little m is at rest, then it will be at rest there, because the gravitational attraction of the ring to this m is 0. Because it just, imagine if here's a dm, it's going to point out this way, and the other will put opposite direction, same magnitude. This cancels out. So this guy will be very peaceful. However, if the question is, how do we let this little m escape this ring? Then we have to let this one acquire a VESP, just like the problem we discussed before. How large has to be the escape speed that we can get out of the gravitational field of the ring and going very far away? The problem is, well, we have to think about this. If this m reaches here, it still has a little speed left. And we hope that it will continue to go to further away. And right now, we know that if little m is right here, there is a gravitational attraction from the ring towards this direction. And we actually obtained that formula. And we can take a look at it. We got it. The gravitational force between the ring and a point mass of a distance a away from it is this. So be careful, this a right now is a variable. So we have to rewrite it. Now how do we rewrite it? The gravitational force right now, I should write as F of G, that is between the ring and point mass, equals to of capital G, little m, and the ring, and divide by, well, there is, let's make this is a variable x, because it's x meters away from the center of the ring, so that will be x, and then the denominator will be at r squared plus x squared and 3 to the 2. And that is the gravitational attraction between the little m and the ring. So the gravitational force is rather complicated. As you can see, when the little m goes further away, when x gets larger and larger, the gravitational force will be weaker and weaker. But anyway, there is a gravitational attraction. If there is a gravitational attraction, there must be a potential energy. Now, how do we write the potential energy of point mass m, x meters away from the ring? I think we cannot use the previous one, because the one we got for the spherical symmetric distribution is potential energy, we learned from the previous case, is negative g m1 m2 over separation. But now this is not a spherical distribution, so we have to start from scratch. How do we do that? That is this. Work done by gravitational force should be expressed as work done is F of G dot D, in this case is dx, because we only move in one direction. Work done equals to the negative change of potential energy. Change is the potential energy final minus potential energy of initial. So from there, we can find our potential energy initial final. So we have to work on it, and let's take a look at what's going to happen. Fg is this way, and our dx is opposite. So this dot production gives us a negative, and we're plugging Fg expression, capital G mm of x over r squared plus x squared of 3 over 2 of dx. That looks pretty good. Why is that? That is because we have a x dx. If we time it 2, divide by 2, then we can have a situation. Here's a negative sign. G comes out, little m, capital M. And this 2, these are constant. And if I regroup 2x dx, that will be dx of square. And denominator is r squared plus x squared of 3 to the 2. As we know, because r is a constant, actually we can do that. So this gives a situation as, well, constant still remains in front of that. We have something like r squared plus x squared. If we bring denominator to the numerator, it's negative 3 over 2 of d r squared plus x squared sum integral. So for this integral, the result should come out as 1 over the coefficient is negative 3 over 2 plus 1 and r squared plus x squared negative 3 over 2 plus 1, right? Let's continue. So the result is the gravitational, the work done by gravitational force equals to negative g, little m, capital M over 2. And the coefficient is, as a matter of fact, plus 1, 2, 2. That will be a negative 1/2 on the denominator, so it's a negative 2 right here. And then we have this negative 1/2, so that will be r squared plus x squared of this one, negative 1/2. From where to where? Well, obviously, let's say from point of x to infinite. When we plug in that infinite, that this is this will be a 0. And then when we plug in x, that will be this. So as a matter of fact, as we can see, the result is negative 2, negative 2, this cancels out. So this will be of GMM, a situation of final, that is this, minus initial is x meters away, so r squared plus x squared, final minus initial, that's that. If we compare this to the work done by gravitational force, equals the negative change of that u final minus u initial. As a matter of fact, what we can do is we need a negative here. So we need a negative here and there. See, this, there. So, see, it's negative, negative. Final is this, minus initial. This tells us u final is negative r squared plus infinite square root. U initial is negative, that's that, r squared plus x squared square root. What does that tell us? That tells us when the little m is x meters away from the ring, its potential energy U of x is negative, as we can see from here, right? Let's don't forget about our constant here, GMM. So it's negative GMM over r squared plus x squared square root. That is the expression of the, I should add this constant here, GMM, GMM. So that is the potential energy right here. So since we know the potential energy right here is this much, and we assume, if we assume x equals 0, then it will bring this guy to here. So the potential energy at the center of the ring, see, when x equals 0, it doesn't equal to 0. When x equals 0, it comes out negative GMM over r. Isn't that interesting? The gravitational force between the ring and M, if M is at the center of the ring, is 0. But it does have a potential energy, which is, when x equals 0, negative gmm over r. And then this has a escape speed. So the energy right here we can write as kinetic is 1/2 mVESP squared. Potential is negative of gmm over r. This is the total mechanical. If we want this one to go further away, well, how far away? Infinite far away. As we learned, when it's infinite far away, this will be 0, right? Because this denominator is so big, it's 0. Potential 0, you barely reach there, no speed. So it's, at the end, it's 0 plus 0. So from here, you can find escape speed. So little m again, both side equation divide by that. You can find VESP equals to F twice gmm over r square root. Very interesting result. Let's look at another problem. Along the x-axis, we have Earth located at the 0 of the x, and we have Earth's moon distance, and we have a moon located here. Question number 1 is, at which point between Earth and the moon the gravitational attraction from the Earth and from the moon cancels out? Well, Earth is very large. Earth has 100 times mass of the moon. So therefore, I guess this is the point that the gravitational attraction from the Earth, which is this way, F of E, cancels with gravitational force from the moon, which is F of the moon. Because for large mass, you need a larger distance to get equal magnitude of smaller mass attraction. So gravitational attraction between the Earth and, let's say, the mass of a space probe is little m. So the gravitational attraction of F of E equals to capital G, mass of the Earth and mass of the space probe divided by x meters. That is the distance between the Earth and this particular location. So separation square. And gravitational force from the moon to the space probe, F of the moon equals to capital G, mass of the moon, mass space probe, and what's there left? That is the Earth's moon distance, subtract the x and square. So if we want to find this x, which is where between the Earth and the moon that the force from the gravitational force from the Earth cancels gravity from the moon, then we just let this one equals that one. We can solve this equation for the x. Assume we already solved that. Now the question is, what is the minimum speed that we need to give to this space probe, that we can let this space probe get into near the moon and then start to circle around the moon as a moon satellite? We need to approach this problem by the energy method. Let's ask this question. What is the total mechanical energy of this space probe at the initial position? It is under influence Earth's gravity. So it is gravitational potential energy between the space probe and Earth. It is also under the influence of the moon. So we have negative G, mass of the Earth, mass of space probe, over x. That's potential energy between the probe and Earth. Potential energy between the moon and space probe. That is RE of the moon, subtract x. That's the potential energy between space probe and moon. And we ask for what is the minimum of speed it requires, so we give a speed. 1/2 mv minimum. That's the total of mechanical energy at that point. Now, if we allow this space probe to be a near moon satellite. Let's say the circular orbit is almost near the radius of the moon. Then, once that happens, it certainly has potential energy. Let's say near the moon will be negative of g mass of the moon, space probe, RE of the moon. If we still think it is under Earth's influence, then we have negative g mass of the Earth. And this is now how far away from the Earth? A moon Earth distance away. That is 2 turns. And then plus the kinetic energy, because this satellite is orbiting. So 1/2 of mass of the space probe, v of the orbital speed square. Now, as a matter of fact, we learned that before. Something circle around, something is in orbit due to the gravitational attraction of a spherical object. The combination of these two terms, actually comes out as this can be replaced by that. The total mechanical around, if something is in a circular orbit around a spherical symmetric distribution, total mechanical is this much. So as we can see, throughout this equation, mass of the space probe cancels. All we need to do is, since from first step number 1, we already solved x, so x is unknown. All we need to do is now we're going to solve what's the minimum speed we need to give to the space probe, because right now the space probe is at rest because FE cancels with FM. Now we need to give a little bit of boost, okay, and we need to give a minimum speed. So once space probe moves towards the moon, then moon force will be larger than the Earth force. It will start to approach the moon. So eventually it's going to settle into the orbit very close to the surface of the moon and become a satellite.